December 30th, 2025. The final hours of a year that will be remembered not for what was announced about, but for what was whispered. Not for the headlines that screamed across news feeds, but for the data that accumulated quietly in astronomical databases while the world celebrated holidays and planned resolutions and remained blissfully unaware that the most significant event in human history might have just occurred, might have passed us by, might have been documented and catalogued and filed away without anyone fully grasping what it meant, what it means, what it will mean when we finally process the implications of what just happened in the darkness beyond our planet. The guest arrived. That's the simple version, the sanitized version that fits into comfortable frameworks and doesn't disturb the sleep of people who prefer their universe predictable and empty. An interstellar object designated 3I Atlas entered our solar system, passed through, and is now leaving. Third such visitor on record. Detected, tracked, studied. Science proceeds as usual. Papers will be published. Data will be analysed. The astronomical community will debate composition and trajectory and whether it fits existing models of cometary behaviour, normal science, business as usual, except it's not. Because when you actually examine what happened, when you look at the timeline and the trajectory and the sheer impossible silence that accompanied this visitor's passage, when you calculate what the detection of this single object implies about the population it represents, you're forced to confront a reality so vast and so terrifying that your brain initially refuses to process it, rejects it as impossible, as too large to be real, as the kind of number that must be wrong, because if it were right, then everything we thought we understood about our cosmic isolation would collapse. Before we go further, before we dive into the mathematics that will reshape how you think about the space around our planet, I need you to do something. Subscribe to this channel right now. Hit that notification bell, because what we're about to discuss isn't being covered adequately anywhere else. The implications are too uncomfortable. The questions too profound. But the data is real and the calculations are reproducible, and if you want to follow this investigation as it develops through 2026, as more observations accumulate and as the uncomfortable truth becomes impossible to ignore, you need to be here. This is not speculation. This is analysis of documented observations leading to conclusions that change everything. The timeline is what breaks the comfortable narrative first. Because 3I Atlas wasn't just passing through, wasn't just a visitor that arrived recently and will leave soon. It's been here, has been drifting through the outer reaches of our solar system for 8,000 years, 8 millennia, since before recorded history began, since humans were still figuring out agriculture and building the first cities and inventing writing. This object has been here, moving among the outer planets and the Kuiper Belt and the scattered disk, a silent ghost in the darkness, present but undetected, watching or drifting or executing whatever mission it might have, if any, while human civilization rose from bronze to iron to steam to nuclear to digital without ever knowing this visitor was there. July 1st, 2025. That's when we finally noticed. When our telescopes finally caught the faint reflection of sunlight off this object as it moved through a region we happened to be surveying. And even then, even with all our vaunted planetary defense networks and sky surveys and asteroid tracking systems, we almost missed it. Would have missed it if the timing had been slightly different, if the trajectory had passed through different coordinates, if luck hadn't aligned such that human eyes, mechanical eyes, happened to be pointing in the right direction at the right time. Think about what that means. We pride ourselves on awareness, on surveillance, on knowing what's in our cosmic neighborhood and tracking potential threats. We've invested billions in detection systems. We've catalogued hundreds of thousands of asteroids and comets. We think we have eyes on the sky. And yet this object, moving at velocities that mark it unmistakably as interstellar, that identify it immediately as not one of ours, managed to be here for 8,000 years before we spotted it, managed to drift through the outer solar system undetected while we congratulated ourselves on our observational capabilities. What else is out there that we haven't seen? That question becomes unavoidable once you grasp the timeline. If one object can be present for 8 millennia without detection, how many others might there be? How many visitors are currently in our solar system right now, this moment, moving through regions we don't survey frequently enough, or at wavelengths we don't monitor, or with reflectivity too low for our current instruments to detect? How blind are we actually? How much traffic passes through while we remain completely unaware? The trajectory tells you immediately this isn't local. Even without detailed composition analysis or spectroscopy or any of the sophisticated measurements we'd like to make, the path alone is diagnostic. Most objects in our solar system follow elliptical orbits, closed curves, bound to the sun by gravity. They swing around in predictable patterns, approach perihelion, recede to aphelion, return again on schedules we can calculate centuries in advance. Clockwork, deterministic, captive. 3i Atlas doesn't do that. Its path is hyperbolic, open curve, not bound, traveling fast enough that the sun's gravity, massive as it is, can't capture it, can bend the trajectory, can deflect it slightly as the object swings past but can't hold it, can't force it into closed orbit. The velocity is too high, the energy too great. This object came from beyond and is returning to beyond, is just passing through. A visitor, not a resident. And that velocity is the smoking gun. When you measure how fast something is moving and you calculate the orbital energy and you determine whether that energy is positive or negative, whether the object is bound or unbound, you get a definitive answer. Local objects, objects that formed in our solar system, have negative orbital energy. They're gravitationally bound, can't escape without something giving them a push. But interstellar objects have positive orbital energy. They're moving faster than escape velocity. They came from elsewhere and they're going elsewhere, and our sun is just a temporary gravitational influence along their journey. 3i Atlas is moving far too fast to be local. Definitively, unambiguously, this is not one of ours. Never was. Formed around some other star in some other protoplanetary disk under conditions potentially very different from what our solar system experienced. And somehow, through mechanisms we can only speculate about, it got ejected, got thrown out of its home system with enough velocity to escape that star's gravity and drift through interstellar space until it happened to encounter our sun. That alone would be fascinating. The third confirmed interstellar visitor, adding to the small but growing catalogue of objects we've detected that definitely originated elsewhere. Oumuamua in 2017, 2i Borisov in 2019, now 3i Atlas in 2025, 3 detections in 8 years. That's a rate, that's statistics beginning to accumulate. That's the foundation of the calculation that will break your intuition about how empty space actually is. October 29th, 2025. Perihelion, closest approach to the Sun. The object passed at 203 million kilometers. For context, Earth orbits at 150 million kilometers from the Sun. 1 astronomical unit. 3i Atlas came within 1.36 AU, not particularly close by solar system standards. Well outside Earth's orbit, no danger of collision, no threat, just close enough that solar heating would be significant. Close enough that if this were a normal comet composed of the volatile ices that comets are made from, we'd expect to see activity, sublimation, outgassing, a visible coma and tail forming as the ice turns to gas under solar radiation. We trained every available instrument on it during this passage: Hubble, ground-based observatories, radio telescopes, infrared detectors, the full suite of astronomical hardware we could bring to bear on a target that was only going to be this close once. This was our chance, our opportunity to gather data while the object was bright enough and close enough to actually measure properties rather than just detecting its existence. And what we found, or rather what we didn't find, is what makes this object profoundly strange. Because 3i Atlas didn't flare up the way comets do, didn't produce the dramatic outgassing and tail formation that we associate with cometary perihelion passages. It remained dim, remained compact, showed minimal activity compared to what we'd expect from a kilometer-scale ball of dirty ice being heated by the sun at that distance. This behavioral anomaly forces uncomfortable questions. If it's a comet, why isn't it acting like one? If it's made of ice and dust, the standard cometary composition, why isn't it sublimating vigorously when exposed to solar heating? Natural explanations exist. Maybe it's covered in a crust, a layer of non-volatile material that insulates the interior and prevents sublimation. Maybe the ice has already been depleted from previous perihelion passages in other stellar systems. Maybe the composition is unusual, dominated by materials that don't sublimate at the temperatures reached during this pass. Each explanation is plausible. Each fits within natural frameworks, but each requires assumptions, requires the object to be special in some way, different from typical comets. And when you're constantly invoking special circumstances to explain observations, when you're stacking assumptions to make the natural explanation work, you start to wonder whether the natural explanation is actually correct, or whether you're forcing data into a framework it doesn't naturally fit. The alternative is what makes everyone uncomfortable. If it's not a comet, if the lack of activity isn't explained by unusual composition or surface crusting or depletion of volatiles, then what is it? What else would look like a small, dark object moving on an interstellar trajectory but not outgassing when heated? What else would remain dim and compact when natural processes predict bright coma formation? A rock could do it, solid asteroid rather than icy comet, just a chunk of stone or metal that happens to be passing through. No volatiles to sublimate, no activity expected. Perfectly natural explanation that requires no special pleading, except we don't typically see asteroids on hyperbolic trajectories. Don't have good formation mechanisms for how rocky bodies get ejected from stellar systems at escape velocity. Ice can be ejected easily, gets gravitationally scattered by giant planets during system formation. But rock, that's harder, requires more energetic processes, or something else entirely, something that doesn't sublimate because it's not made of ice, that remains compact because it's coherent, that shows no tail because it produces no exhaust, something designed and built rather than naturally formed, artificial rather than natural, technology rather than geology. And now we're in territory that makes scientists nervous, makes peer reviewers skeptical, makes the public either excited or dismissive depending on their priors about whether intelligent life exists beyond Earth and whether it builds things and sends them to other star systems. We're asking whether 3I Atlas might be artificial, whether it might be a probe, whether the cosmic date might have been not with a random piece of debris but with a messenger from beyond. The data doesn't prove it, doesn't provide smoking gun evidence that forces that conclusion. But the data also doesn't rule it out, doesn't provide clear natural explanation that makes the artificial hypothesis unnecessary. We're in the uncomfortable space of genuine ambiguity, where multiple interpretations remain viable, and where conclusions depend on assumptions you bring to the analysis, rather than being forced by observations alone. But here's where it gets truly mind-bending, where the implications expand from interesting anomalous object to restructuring our entire understanding of the cosmos. Because whether 3I Atlas is natural or artificial, whether it's a comet or a probe, its detection tells us something profound about population statistics, about how many objects are out there that we're not detecting, about what the existence of 3 interstellar visitors in 8 years implies about the total number moving through the galaxy at any given moment. This is where we need to run the numbers, where we need to take the single data point of 3I Atlas, combine it with Oumuamua and 2I Borisov, and extrapolate to estimate the population those detections represent. And when you do that calculation, when you apply the standard statistical methods for inferring population from sampling, you get an answer that's so large it seems impossible. That makes you check the math repeatedly, because surely there must be an error. Surely the number can't actually be that big. Let's assume for the moment that these objects are natural, that they're comets and asteroids ejected from other stellar systems through ordinary gravitational scattering, that their presence here is the result of random processes operating across the galaxy over billions of years. If that's true, if we're sampling from a random distribution, then the detection of 3 objects in 8 years from our limited survey capabilities tells us about the underlying density of these objects in interstellar space. The calculation requires knowing several things. How much volume of space can our telescopes survey? How faint an object can we detect at various distances? How long are we actually looking, accounting for weather and telescope time allocation and all the practical limitations that reduce effective observation time? And given those detection capabilities, what population density would produce the observed detection rate of roughly 1 object every 3 years? When you plug in the numbers, when you account for the survey volume and the detection thresholds and the time baselines, you get an estimate for how many interstellar objects are passing through our solar system at any given time. And the answer is stunning, is literally difficult to comprehend, because the calculation suggests that right now, at this moment, there may be 1 trillion such objects present within the volume we call our solar system, extending from the Sun out to the edge of the Oort cloud at roughly 100,000 astronomical units. 1 trillion, 10 May 12, 1,000 billion. That's not a typo. That's not exaggeration for dramatic effect. That's the statistical estimate based on our detection rate and our survey capabilities. At any given second while you're reading this, there are likely 1 trillion interstellar visitors drifting through the outer reaches of our solar system, through the Oort cloud and the scattered disk and the Kuiper belt. Dark, cold, silent, invisible to our instruments because they're too faint and too far and too small to be detected unless they happen to pass close to the Sun where reflected light makes them visible. 3i Atlas is just the one that got close enough and bright enough to be spotted, the one that happened to pass through the inner solar system where our detection capabilities are strongest. But for every one we detect, there are trillions we miss. Trillions that pass through the outer regions without ever coming close enough to be seen. That drift through our cosmic neighborhood completely unnoticed because they're beyond our detection range. And this is assuming they're natural, assuming they're passive rocks and ice balls following purely gravitational trajectories. If that assumption is correct, if the trillion object estimate represents reality, then we need to explain where all these objects came from. How the galaxy produced this enormous population, what mechanisms ejected so much material from so many stellar systems that interstellar space is filled with wandering debris. The mass budget is staggering. If there are 1 trillion objects in our solar system alone, and if you scale that up to the galactic level, if every star system is hosting similar populations, then the total number of interstellar objects in the Milky Way is approximately 10^23. That's a 1 followed by 23 zeros. That's comparable to the number of stars in the observable universe, but all in our single galaxy, all in the form of wandering comets and asteroids drifting between stars. To create that population, to sustain it over billions of years against losses as objects collide or get captured or fall into stars, requires continuous production, requires every star system in the galaxy to be ejecting material at prodigious rates, requires that planetary formation is incredibly wasteful, that for every planet that forms and stays in orbit, dozens or hundreds of planetary embryos get scattered and ejected, that the galaxy has processed the equivalent of 3 million solar masses of material over its lifetime just to maintain this ocean of wanderers. 3 million suns worth of rock and ice, broken into trillions upon trillions of pieces, drifting through the void. That's what the natural hypothesis requires. That's the implication of our detection rate if these objects are just random debris. And while that's not impossible, while stellar system formation is indeed wasteful and does eject material, the sheer scale strains credibility, makes you wonder whether we're missing something, whether the model is incomplete, whether there might be other sources or other explanations for why we're detecting these objects at the rate we are. But here's the truly unsettling part, the part that keeps me awake thinking about implications. If the trillion object estimate is correct, if our solar system really is swimming in this ocean of interstellar visitors, then Earth has been bombarded by close encounters for its entire existence. Over the 4.5 billion year lifetime of our planet, the calculation suggests there may have been 1 billion close approaches. 1 billion times that an interstellar object passed within the inner solar system, within distances where impacts were possible, where gravitational effects were significant, where, if the object carried anything interesting like complex organic molecules or even microbial life, transfer to Earth might have occurred. 1 billion cosmic dates, 1 billion visitors, and we missed them all. Remained completely unaware of this traffic because we didn't have eyes that could see, and because we didn't exist for most of Earth's history, and because even when we did exist, even when humans were around and watching the sky and wondering about lights in the darkness, these objects were invisible, too faint, too fast, too easily confused with stars or planets or other familiar sky features. We've been standing in the middle of a busy intersection during rush hour, blindfolded, convinced we were alone, convinced the street was empty, while traffic rushed past in volumes we never imagined, while the universe was far more dynamic and far more populated than our limited observations suggested, while our isolation was illusion created by inadequate detection capabilities rather than actual absence of visitors. Does that make you feel more connected to the galaxy or more vulnerable? That's not a rhetorical question. That's genuine inquiry, because the answer affects how we should respond. If the presence of 1 trillion interstellar objects in our solar system means we're part of a galactic ecosystem, that we're connected to other stellar systems through this traffic of wandering matter, then maybe we should be excited, should embrace our role as one node in a vast network, should recognize that we're not as alone as we feared. But if that presence means we're vulnerable, that we're exposed to whatever these objects might carry or might do, that we're swimming in waters we don't understand filled with things we can't see, then maybe fear is appropriate response. Maybe we should be alarmed that we've been blind for so long, that we've lived in ignorance of cosmic environment that might pose risks we haven't evaluated. Both responses are valid. Both are grounded in the same statistical reality. Both emerge from the same calculation showing that interstellar visitors are common rather than rare, that our detection of 3 in 8 years implies enormous underlying population. That space around us is far from empty, even if it looks empty to our inadequate eyes. But all of this, all the trillion object calculation and the billion close encounters and the 3 million solar masses of processed material, all of it rests on one critical assumption, that these objects are natural, that they're random wanderers following purely gravitational trajectories determined by chance rather than choice. That 3I Atlas and Oumuamua and 2I Borisov are pieces of driftwood in cosmic currents rather than ships with destinations. What if that assumption is wrong? What if some fraction of these objects, even a tiny fraction, are artificial? What if they're not debris but deliberate? What if they're probes or sensors or communication relays or infrastructure built by civilizations that learned how to cross interstellar space and that seeded the galaxy with hardware we're only now beginning to detect? Then everything changes. Then we're not calculating population of random debris. We're calculating population of a network. We're not swimming in wreckage. We're swimming in presence of intelligence that operates on scales we barely comprehend. And the question shifts from, what is this object, to what is it doing and who sent it and what does its presence here mean for us? The trillion object estimate based on natural hypothesis is already disturbing. Already forces us to revise our understanding of how dynamic the galaxy is. But it's explainable. Fits within frameworks we understand. Results from well-known processes operating over long timescales. We can build models, can calculate where the material came from and how it got here and what trajectories it follows. can make it all work within conventional astrophysics, even if the numbers are uncomfortably large. But if these objects are artificial, if they represent technology rather than geology, then conventional frameworks don't apply. Then we're not calculating based on planetary formation efficiency and gravitational scattering rates. We're calculating based on intent, on design, on decisions made by minds we've never encountered about how to explore or monitor or communicate across the vast distances between stars. And that calculation is completely different, because technology isn't randomly distributed, isn't following gravitational trajectories determined by initial conditions billions of years ago. Technology goes where it's sent, operates according to programming, executes missions defined by creators who had purposes and goals and reasons for building what they built and sending it where they sent it. If 3I Atlas is artificial, if it's here by design rather than by chance, then its trajectory isn't random sample from distribution of wanderers. It's chosen, it's deliberate, and that means something. Might mean our solar system was specifically targeted, might mean Earth is point of interest, might mean someone, somewhere, sometime decided that this corner of the galaxy was worth visiting and built hardware to make that visit happen. The implications cascade from that possibility, because if we're being visited deliberately, if these objects are arriving with purpose rather than drifting through randomly, then we're not alone in passive sense of life exists elsewhere. We're not alone in active sense of intelligence has noticed us and is doing something about it. We're known, we're catalogued, we're potentially being monitored or studied or evaluated according to criteria we don't understand by entities we've never met. And if our solar system is hosting artificial visitors, if some fraction of that trillion object population represents probes rather than rocks, then the numbers change completely. We don't need 3 million solar masses of ejected material to explain the population. We need industrial capacity. We need civilizations capable of building millions of probes and sending them out across the galaxy on missions that last millions of years. We need Kardashev scale thinking about energy budgets and construction capabilities that make human space programs look like children playing with model rockets. This is the pivot point, the place where analysis splits based on whether you think artificial origin is plausible or not, because all the subsequent reasoning depends on that choice. If natural, you calculate populations based on astrophysical processes. If artificial, you calculate based on technological capabilities and strategic decisions about galactic exploration. And here's the deeply uncomfortable truth. We don't have enough data to definitively choose, don't have smoking gun evidence that forces conclusion one way or the other. We have suggestive features, anomalies that don't quite fit natural models, behaviors that look potentially organized, but nothing definitive, nothing that proves technology versus exotic natural processes. So we're left with probabilities, with Bayesian reasoning about which explanation is more likely given the observations and given our prior beliefs about how common intelligence is and whether civilizations build and send interstellar probes. And different researchers looking at the same data reach different conclusions based on those priors, based on what they think is probable about the universe before they examine any specific observation. This is uncomfortable for science because science is supposed to be objective, supposed to reach conclusions based purely on data without prejudice from prior beliefs. But in practice, when data is ambiguous, priors matter enormously. Shape how we interpret observations, determine whether we find natural explanations satisfying or whether we think artificial possibilities deserve serious consideration. The detection of 3I Atlas doesn't resolve these questions, doesn't provide clarity. What it does is make them urgent, makes them immediate, forces us to confront possibilities we might prefer to defer until we have better data, because the object is here now. The detection has happened, and the implications, whether natural or artificial, demand response. Demand that we think seriously about what this means and what we should do about it. The technological hypothesis isn't fringe speculation anymore, isn't the domain of enthusiasts who see aliens behind every anomaly. It's being discussed in peer-reviewed journals, being presented at professional conferences, being evaluated by credentialed researchers who are applying the same rigor to artificial possibilities that they apply to natural ones. And that shift, that transition from dismissing technological origin automatically to treating it as legitimate hypothesis worthy of investigation is itself significant, is recognition that the data we're collecting doesn't cleanly favor natural explanations, that the anomalies are real and persistent, and that we owe it to intellectual honesty to consider all possibilities rather than reflexively defending comfortable assumptions. So let's examine the artificial hypothesis seriously. Let's look at what observations would support it and what mechanisms it would invoke and how it changes the interpretation of everything we've seen. Because if 3I Atlas is technology, if it's a probe sent by some civilization that learned how to cross interstellar space, then every feature we've documented takes on different meaning, stops being geology and becomes engineering, stops being chaos and becomes design. The motion is where the artificial hypothesis gets traction, because when 3I Atlas passed perihelion, when it swung closest to the Sun, the trajectory showed subtle deviations from pure gravitational prediction. Not large, not the kind of dramatic course changes that would be unmistakable, but measurable, detectable. Small accelerations that don't quite match what gravity alone should produce. Anomalies that require explanation. For a natural comet, the standard explanation is outgassing, jets of sublimating ice creating thrust, pushing the object off its predicted path. This is well-documented physics. We see it constantly in comets. Calculate the forces, model the trajectories, account for the deviations. It works, it's normal. But 3I Atlas didn't show normal outgassing, didn't produce visible coma or tail, didn't exhibit the signatures of vigorous sublimation that we'd expect if gas jets were strong enough to create measurable thrust. So if it's not outgassing creating the acceleration anomalies, what is? Where is the force coming from that's pushing the object off the purely gravitational path? The solar sail hypothesis is what bridges from natural to artificial. Because there's a mechanism, physically real and perfectly understood, that can create thrust without producing exhaust, without leaving visible signatures of propulsion, radiation pressure, the momentum carried by photons from the sun, light pushing against surfaces, creating force that depends on area and reflectivity, but not on mass ejection. For normal objects, for chunks of rock and ice with typical shapes and surface properties, radiation pressure is negligible, too weak to create measurable trajectory changes. The force is there, but it's swamped by gravity and by any actual propulsion from outgassing. You can detect it in careful analysis, but it's a small correction term rather than a dominant effect. But for certain geometries, for objects that are very thin and very reflective, radiation pressure can become significant, can create accelerations that are measurable, that affect trajectories in ways that look like propulsion, even though there's no engine and no exhaust, just photons bouncing off a large light-collecting surface and transferring momentum. We've built solar sails, know they work, have launched spacecraft that use sunlight for propulsion rather than carrying fuel. It's established technology at human scale, and if we can do it with our primitive capabilities, if we can build thin, reflective surfaces that catch sunlight and accelerate spacecraft, then surely a civilization more advanced than us could do it better. Could build larger sails, more efficient surfaces, structures that maximize thrust while minimizing mass. If 3I Atlas were such a structure, if it were a solar sail rather than a rock, it would explain the acceleration anomalies perfectly, would explain why we see thrust without seeing exhaust, would explain why the object doesn't outgas like a normal comet. Because it's not a comet, it's technology. It's engineered hardware using understood physics to navigate through stellar systems without needing to carry propellant. And this isn't new speculation. We saw exactly the same arguments with Oumuamua. The first interstellar visitor showed even more dramatic acceleration anomalies, even less evidence of outgassing to explain them. And researchers, including serious academics at prestigious institutions, proposed that Oumuamua might be artificial, might be a light sail, might be exactly the kind of probe that a spacefaring civilization would build if it wanted to visit other star systems. The proposal was controversial, still is. Most of the astronomical community remains skeptical, prefers to believe that exotic but natural explanations will eventually account for Oumuamua's properties, even if we haven't found those explanations yet. But the artificial hypothesis wasn't dismissed, wasn't rejected out of hand. It was published, discussed, evaluated, and it remains on the table as a possibility that fits the observations at least as well as the natural alternatives do. Now we have 3i Atlas showing similar anomalies, similar pattern of acceleration without obvious outgassing, similar features that strain natural explanations while fitting technological ones. And the pattern across multiple objects, the fact that we're seeing this consistently in interstellar visitors rather than just once in Oumuamua, strengthens the case, makes coincidence less likely, makes it harder to argue that each object independently happens to have exotic natural properties that mimic what we'd expect from technology. But there's deeper implication if the technological hypothesis is correct. If 3i Atlas and possibly Oumuamua and potentially some fraction of the trillion objects we calculated are artificial rather than natural, because then we're not dealing with random traffic. We're not swimming in debris ejected chaotically from forming planetary systems. We're dealing with deliberate presence, with infrastructure, with network. Think about how we explore space. We send probes, Voyager, Pioneer, New Horizons, Cassini, Juno, dozens of spacecraft over the decades, each designed for specific mission, each carrying instruments chosen to answer particular questions. We don't send one. We send many. Because space is vast and there's much to study, and redundancy matters when missions last decades and when you can't service or repair anything once it's launched. Now imagine a civilization that's been spacefaring not for decades but for millions of years, that has energy resources and construction capabilities far beyond anything we can achieve, that thinks on timescales where century-long missions are brief, that has automated manufacturing and self-replicating systems and infrastructure that spans stellar systems. What would their exploration program look like? They wouldn't send one probe. They'd send millions. Billions, maybe. They'd seed the galaxy with sensors, with communication relays, with automated systems that drift between stars gathering data about stellar systems they pass through. They'd build a network, a galactic-scale observation infrastructure that collects information continuously over millions of years and transmits it back to wherever the civilization is located, or stores it for later retrieval, or processes it autonomously depending on what the mission parameters specify. This is the vision that emerges if you take technological hypothesis seriously, if you accept that some fraction of interstellar visitors are artificial, and you extrapolate what that means about the builders and their capabilities and their goals. You get picture of galaxy that's not empty of intelligence, not virgin territory waiting for first civilization to expand into it, but instead a space that's already populated with infrastructure, with hardware, with presence of minds that might be vastly older and more capable than ours, even if those minds are now distributed across machines rather than residing in biological bodies. And if that picture is accurate, if the galaxy is crisscrossed by probe networks from multiple civilizations that arose millions or billions of years ago, and that seeded space with their technology, then our detection of 3 interstellar visitors in 8 years isn't surprising, isn't even particularly remarkable. It's expected, it's inevitable. We've finally developed instruments sensitive enough to detect what's been here all along, have finally opened our eyes enough to see that we're not alone and never were. The trillion object calculation takes on completely different meaning in this context. Because if those aren't natural wanderers but are instead components of technological networks, then 1 trillion objects in our solar system at any given time isn't an absurdly large population that strains credibility. It's exactly what you'd expect from civilizations that think big, that build infrastructure on scales that make human engineering look like amateur hour, that can afford to have thousands or millions of probes per star system because they've solved the manufacturing and deployment problems, and because gathering data from every stellar system in the galaxy is worth the investment. From this perspective, Earth hasn't been bombarded by random debris over its lifetime. It's been surveyed, continuously, persistently, by automated systems that pass through regularly gathering data about our planet and our sun and our biosphere. That might have watched life emerge, might have monitored evolution, might be watching now as technological civilization develops and begins its own tentative steps toward becoming spacefaring species. This is surveillance hypothesis, and it's uncomfortable for obvious reasons, because being watched implies watchers, implies that our privacy, our isolation, our assumption that what we do on our planet is our own business, all of that is illusion. If there are probes here monitoring us, then our history isn't private, our development isn't unobserved. Someone or something knows we're here and has been keeping track. But maybe that's okay. Maybe being noticed is better than being alone. Maybe knowing that intelligence exists beyond Earth, and that it's capable of building things that last millions of years, and that it's interested enough in our corner of the galaxy to send probes is cause for optimism rather than concern. Maybe the network exists not for control or threat, but for knowledge, for understanding, for building picture of how life evolves and how civilizations develop across the full diversity of stellar systems in the galaxy. We do the same thing at smaller scale. We send probes to planets and moons in our own solar system. We study them. We document their geology and atmospheres and whether they might harbor life. We don't do this because we want to control or threaten. We do it because we're curious, because understanding the universe is intrinsically valuable, because knowledge matters. If galactic civilizations think the same way, if curiosity and the drive to understand are universal rather than just human traits, then the probe networks make sense. Our natural extension of scientific inquiry scaled up to galactic dimensions are exactly what we'd build if we had the capability and the time and the resources to do it properly. But there's also darker possibility, that the probes aren't just sensors, that they're not merely collecting data for scientific databases somewhere, that they serve strategic purposes: defense, early warning, resource assessment, evaluation of potential threats or opportunities, that the networks exist not just to observe, but to control, to manage, to ensure that young civilizations like ours don't do anything that affects the galactic status quo in ways the older civilizations don't want. This is the zoo hypothesis, the idea that Earth is being monitored to ensure we don't break quarantine, don't expand beyond our designated boundaries, don't develop technologies or behaviors that are deemed threatening by civilizations that were here first and that established rules we're not aware of, that our isolation isn't natural but is enforced, that the apparent absence of contact isn't because intelligence is rare but because contact is prevented, that we're being kept in a cage we can't see by entities we can't detect using methods we don't understand. These speculations run far beyond what the data supports, beyond what we can conclude from detecting 3 objects with anomalous properties, but they're logical extensions of taking the technological hypothesis seriously, of following the implications wherever they lead rather than stopping at comfortable conclusions. If even one interstellar visitor is artificial, if that's proven beyond reasonable doubt, then we have to confront what that means, have to think about who built it and why, and what their presence implies about our situation. And that thinking is uncomfortable, forces questions we don't have answers to, questions about power and knowledge and age and capability and intent, questions about whether being noticed is good or bad, whether we should be trying to make contact or trying to hide, whether the probes are friendly or neutral or potentially hostile, Whether we're ready for implications of confirmed technological presence from beyond, or whether we should be hoping the natural explanations turn out correct so we can defer these questions for another generation. The classification challenge is where philosophy meets practice. Because even if we accept that some interstellar visitors might be artificial, even if we take that possibility seriously enough to look for evidence, we still need to distinguish which objects are actually worth investigating versus which are just rocks. We can't chase everything, don't have resources, don't have time, don't have spacecraft capable of matching the velocities these objects travel at and intercepting them before they leave the solar system. We need filter, need way to look at detection, at a faint dot moving across star fields, and make intelligent decision about whether it's worth the enormous investment required to study it closely, need to separate signal from noise, need to identify the objects that have highest probability of being artificial or at least unusual enough that close investigation might yield discoveries that justify the cost. This is where the proposed Loeb scale comes from, named after the researcher who's been most vocal about taking artificial possibilities seriously, who's been arguing for years that we should look for technological signatures in astronomical observations rather than assuming everything is natural. Who proposed the solar sail hypothesis for Oumuamua and who's been developing frameworks for how to evaluate interstellar visitors systematically? The scale is simple. 3 categories: Class C, Class B, Class A. Like grading system, but for cosmic significance rather than academic performance. Each class represents different level of interest based on what properties the object displays and how likely those properties are to indicate artificial origin versus natural processes. Class C is baseline. Standard interstellar comet or asteroid. Shows composition consistent with natural formation. Exhibits behaviors explicable through normal sublimation or rotation or tidal effects. Follows trajectory that's purely gravitational. No anomalies that require special explanation. Interesting scientifically because it's from another stellar system, because studying its composition tells us about conditions elsewhere, but not surprising. Not challenging our models. Just another data point about the diversity of planetary formation across the galaxy. If you detect Class C object, you catalogue it. You make observations if resources permit. You add it to the database of confirmed interstellar visitors. But you don't drop everything. Don't redirect major facilities. Don't launch intercept missions. It's business as usual. Science proceeds normally. Class B is where it gets interesting. These are objects with anomalies, features that don't quite fit standard models. Unusual accelerations like Oumuamua and 3I Atlas show, strange rotation states, high reflectivity suggesting surfaces that aren't typical of natural bodies, composition that's exotic, structural features that look organized, any of the warning signs that natural explanation might be incomplete or might require stacking multiple special circumstances to work. Class B objects deserve attention, deserve intensive study with best available instruments, deserve papers analyzing their properties and debating interpretations. These are the objects that push boundaries of our understanding, that might be natural but unusually so, that might be artificial but ambiguously, that sit in the uncertain space where we don't have enough data to decide conclusively and where getting more data becomes priority. 3I Atlas is solidly Class B, maybe leaning toward higher end of Class B given the multiple independent anomalies, the lack of outgassing despite perihelion passage, the acceleration without obvious propulsion source, the narrow dust grain size distribution, the episodic brightness variations. Stack all those together and you have an object that demands explanation, that resists easy categorization. That might teach us something important about either exotic natural processes or about technological signatures if we study it carefully enough. Class A is the gold standard. The unambiguous case. The object that shows clear, definitive signs of artificiality that can't be explained away through any plausible natural mechanism. Smooth hull instead of a regular surface. Transmission detected at specific frequencies. Maneuvers that aren't explicable through outgassing or radiation pressure or any natural force. Composition that includes refined materials or isotopic ratios that don't occur naturally. Structural features that are obviously manufactured rather than accreted. We haven't found Class A object yet. Oumuamua wasn't quite there. 3i Atlas isn't there. We're still in the realm of suggestive but ambiguous, still able to construct natural explanations, even if they require effort, still short of the smoking gun that would force even skeptics to acknowledge, yes, this is technology, this is artificial, this is proof that intelligence beyond Earth exists and builds things and sends them across interstellar space. But the hope, the vision that drives this classification scheme is that Class A objects exist, that we'll find one if we look carefully enough, that among the trillion interstellar visitors passing through our solar system, at least some are artificial, and at least some of those are distinctive enough that we can recognize them when we see them. That first contact won't be radio transmission from light years away. Will be physical object we can point telescopes at and eventually send spacecraft to, hardware we can touch. The scale isn't just academic exercise, isn't just way to organize thinking about these objects, it's operational tool, it's decision framework for allocating resources, for determining which objects justify launching interceptor missions versus which get routine observation versus which get ignored because resources are limited and we have to prioritize. And this is where it connects to the infrastructure proposals, to the hardware being designed and advocated and potentially built over the next decades. Because if we're serious about finding artificial interstellar visitors, if we actually want to identify Class A objects rather than just speculating about whether they exist, we need capabilities we don't currently have, need to detect these objects earlier, need to see them while they're farther out, need to resolve their shapes and surface features rather than just seeing them as points of light, need to be able to reach them with spacecraft before they leave our solar system. That requires investment. Requires building systems specifically designed for interstellar visitor investigation, requires accepting that this is priority worth dedicating resources to rather than just interesting side project that gets attention when convenient, requires commitment to actually following through on the implications of taking technological hypothesis seriously. The first requirement is detection. We need to see these objects sooner. 3i Atlas was detected in July but had been in our solar system for 8,000 years. That's unacceptable if we want to study these visitors thoroughly. We need to catch them on the way in, need to spot them while they're crossing Jupiter's orbit or farther out, need months or years of warning rather than weeks. That means wide-field sky surveys, telescopes that can scan the entire visible sky repeatedly looking for faint moving objects. Systems like Vera Rubin Observatory that will come online in the next few years and that will revolutionize how we detect transient phenomena and moving objects. But even better than that, more telescopes, more survey programs, more coordinated searching such that nothing bright enough to be detected by current technology passes through without being seen. The survey programs are already being built, already being funded, already ramping up to provide the detection capabilities we need. But there's gap between detection and characterization, between seeing that something is there and understanding what it is. And that gap is what the next layer of infrastructure is designed to bridge. Resolution is where Earth-based telescopes hit their limits, because atmosphere blurs, scatters light, creates turbulence that prevents you from seeing fine details no matter how large your mirror is or how sophisticated your adaptive optics system might be. You can correct for atmospheric distortion to some degree, can remove much of the blurring, but there's fundamental limit set by physics of light passing through turbulent air. You can't completely eliminate it from ground-based observations. For normal astronomy that's usually acceptable, most objects we study are far enough away that atmospheric blurring doesn't prevent us from seeing the features we care about. Galaxies billions of light-years distant, Stars hundreds of light years away. Even planets in our solar system are large enough and close enough that we can resolve surface features through atmosphere if we use the right techniques. But interstellar visitors are different. They're small, kilometer scale or smaller, and they're far. Even at closest approach, even when they pass within Earth's orbit, they're tens or hundreds of millions of kilometers away. The angular size, the apparent diameter as seen from Earth, is tiny, measured in milliseconds, far below what atmospheric turbulence allows you to resolve from ground. So from Earth, these objects are just points of light. You can measure their brightness, can track their position, can do spectroscopy to determine composition, but you can't see their shape, can't resolve whether they're spherical or elongated or flat, can't detect surface features that would distinguish natural irregular asteroid from smooth manufactured hull, can't see the details that would let you definitively classify them. That's the fundamental limitation that needs to be overcome if we want to identify Class A objects with confidence. We need to see them clearly, need images with enough resolution to show shape and surface properties, need to get above the atmosphere or far enough away that atmospheric effects don't dominate. Space telescopes solve this. Hubble, James Webb. Getting above atmosphere lets you achieve diffraction-limited resolution, lets you see details determined only by the size of your mirror and the wavelength of light you're observing. No turbulence, no blurring, just physics of light and optics. But even space telescopes have limits. Size constraints from what you can launch, cost constraints from building and operating complex spacecraft. And even with perfect optics, even with diffraction-limited performance, resolving kilometer-scale object at hundreds of millions of kilometers requires very large aperture, requires mirrors tens of meters across or larger, requires capabilities beyond what we can currently put into space. Unless you build it somewhere that's not Earth, somewhere that has no atmosphere but that has stable surface to build on, somewhere that's close enough to be accessible but far enough that Earth's infrastructure doesn't need to support it continuously, somewhere like the Moon. The Lunar Interferometer proposal is audacious, is exactly the kind of big thinking that transformative projects require. Instead of trying to launch single large telescope into space, instead of fighting the mass and volume constraints of rocket fairings, you build it in place, on the Moon, using lunar materials where possible, assembling it piece by piece over years or decades until you have instrument that couldn't exist any other way. The design is 100 meters baseline, not single mirror, but array of them. Interferometer that combines light from multiple telescopes separated by that distance to create resolution equivalent to telescope 100 meters across. Football field-sized eye that can resolve details far smaller than any single instrument we've built. That can see surface features on objects millions of kilometers away. That can distinguish shapes clearly enough to tell rocks from manufactured structures. Lunar surface provides several advantages. Stable platform, no weather, no atmosphere, no orbital mechanics to worry about. Long lunar day means 2 weeks of continuous observation time before sun rises and floods the site with light. And low gravity means structures can be larger and less massive than equivalent would need to be on Earth, can build things that would collapse under their own weight in terrestrial gravity. The challenges are enormous. Construction on Moon requires infrastructure we don't currently have, requires lunar base with manufacturing capability, requires transportation systems to deliver materials and components, requires power systems to operate the instruments, requires communication systems to transmit data back to Earth, requires solving all the engineering problems of sustained lunar operations that we've been discussing for decades but haven't yet implemented. But the challenges aren't fundamental, aren't physics problems. They're engineering and economics and will. We know how to do this in principle. We have the technology. We lack the funding and the political commitment and the coordinated international effort that would be required to actually build it. But those are solvable problems if the motivation exists, if we collectively decide this is priority worth pursuing. And the lunar eye would be transformative not just for interstellar visitor studies, but for astronomy generally, would provide capabilities that would revolutionize how we observe solar system and beyond, would be the kind of facility that enables discoveries we can't currently anticipate because we don't have access to the observations it would make possible, would be worth building even if interstellar visitors didn't exist, just for the science return it would provide. But for interstellar visitors specifically, for the goal of identifying artificial objects with confidence, it would be game-changing, would provide the resolution needed to see shapes clearly, to distinguish regular natural forms from geometric-designed structures, to detect surface features that indicate manufacturing versus natural formation, to answer the question, is this technology, with visual evidence rather than just statistical arguments about anomalous properties. With lunar eye operational, 3-eye atlas wouldn't be ambiguous Class B object that requires stacking evidence to make case for potential artificial origin. We'd have images, would see whether surface is irregular rocky like natural asteroid or smooth metallic like manufactured hull, would see whether structure is chaotic like accreted rubble pile or organized like engineered craft, would have visual confirmation that either supports or refutes technological hypothesis definitively. That's the vision. That's what the infrastructure proposals are aiming toward. Not just incrementally better detection capabilities, but qualitatively different observational power that changes what's possible. That lets us answer questions that currently remain ambiguous because our instruments aren't adequate. But detection and imaging, as powerful as they are, still leave you observing from distance, still studying these objects remotely through photons that traveled millions of kilometers carrying limited information about their sources. If you really want to know what something is, if you want definitive answers rather than inference based on remote sensing, you need to touch it, need to sample it, need to go there. That's what the Interceptor fleet proposal addresses, the final layer of the infrastructure for studying interstellar visitors. Not just passive observation, but active intervention. Going to these objects while they're passing through our solar system rather than just watching them go by. Matching their velocities, making physical contact, conducting direct analysis that removes ambiguity and provides data that remote observations can't deliver. The mission profile is challenging in ways that normal planetary missions aren't, because planetary missions target objects that are in stable orbits. That will be in predictable locations months or years from now when your spacecraft arrives. That give you time to plan and launch and execute trajectory corrections as needed. That are patient. That wait for you. Interstellar visitors don't wait. They're moving through on hyperbolic trajectories at tens of kilometers per second. They appear. They pass. They leave. If you want to reach them, you need to launch quickly, need to match velocities that are far higher than anything in bound solar system orbit moves at, need propulsion systems capable of accelerating spacecraft to interstellar scale speeds on timescales of weeks or months rather than years. That requires high-thrust engines. Conventional chemical rockets won't do it, don't have enough specific impulse, can't achieve the delta-V needed to catch these objects. Nuclear thermal propulsion might work, using nuclear reactor to heat propellant to very high temperatures before expelling it. Gets you higher exhaust velocities than chemical rockets can achieve. Makes missions possible that chemical couldn't attempt. Electric propulsion is another option. Ion engines or Hall thrusters that accelerate ions using electric fields to very high velocities. Extremely high specific impulse but very low thrust. Takes long time to build up velocity, but if you start from high orbit or from Lagrange point, if you're not fighting planetary gravity, electric propulsion can eventually achieve the speeds needed. Just requires patience and continuous thrust over weeks or months. The Interceptor concept puts small spacecraft at strategic locations. Lagrange points are natural choices. Stable orbits where gravitational forces from Sun and Earth balance such that objects parked there stay put without requiring propulsion. Multiple Lagrange points exist at different locations. Put interceptors at several of them and you have distributed fleet that can respond to visitors approaching from different directions. When detection occurs, when survey telescopes spot new interstellar visitor entering inner solar system, you calculate its trajectory, determine which interceptor is best positioned to reach it, command that spacecraft to launch, execute burn profile that will bring it alongside the visitor at matched velocity where close approach and sampling become possible. The spacecraft itself would be small, doesn't need crew, doesn't need life support, just needs propulsion, power, instruments for close-range analysis, and communication to transmit data home. Robotic probe optimized for this specific mission, built in quantity so multiple interceptors can be deployed to different Lagrange points and launched at different visitors as opportunities arise. The science payload would focus on questions that remote observations can't answer. Surface composition measured directly. Is it rock, ice, metal? Refined alloys that don't occur naturally. Crystalline structures indicating manufacturing versus natural formation. Organic molecules suggesting biological involvement. All the chemical clues that distinguish natural from artificial evolved from designed. Physical samples, if possible. Extending manipulator arm. Scraping surface. Collecting material for onboard analysis or potentially for return to Earth if mission profile allows. Direct touch. Contact that removes all ambiguity about whether object is what remote observations suggest or whether apparent anomalies are just unusual natural properties that we haven't seen before. And imaging at close range, not from millions of kilometers away trying to resolve details through limitations of angular resolution, but from meters or kilometers away where cameras can capture surface features directly, where you can see whether there are craters from impacts or smooth panels, whether there are vents or antennas, whether structure shows randomness of natural formation or organization of deliberate design. This is the missing piece in current capabilities. We can detect these objects, can track them, can observe from distance, but we can't reach them, can't study them up close, can't make the definitive measurements that would settle the natural versus artificial debate conclusively. The interceptor fleet proposal fills that gap, provides the capability to actually investigate rather than just observe. Implementation requires pre-positioning the interceptors before visitors arrive, because there's not time to launch from Earth's surface when detection occurs. Even with most aggressive launch vehicles, even with fastest possible trajectory, you can't go from ground to intercept trajectory in the brief window available. Object is through inner solar system and gone before you could reach it. But if spacecraft are already in space, already at high orbit or Lagrange points where Earth's gravity well isn't constraining them, launch becomes maneuver rather than escape, becomes trajectory adjustment rather than fight against planetary gravity, becomes feasible on the timescales needed to catch visitors before they leave. The fleet doesn't need to be large, doesn't require hundreds of spacecraft. Maybe a dozen interceptors strategically positioned provides adequate coverage. Enough that whichever direction visitor approaches from, at least one interceptor is reasonably positioned to reach it. Enough to respond to multiple visitors if they arrive in close succession. Enough to provide redundancy if some missions fail. Cost is real, but not prohibitive. Building and launching a dozen small robotic spacecraft is expensive but within range of what space agencies already spend on flagship missions. The individual interceptors would be cheaper than Mars rovers or outer planet orbiters because they're simpler, don't need to operate for years, just need to survive weeks or months during transit and close approach, don't need elaborate instruments, just focused payload for answering specific questions about composition and structure. The political challenge is probably harder than technical one, because international coordination would be required. Multiple agencies contributing, shared goals and shared data, no single nation claiming ownership of discoveries or hoarding information about what's found. genuine collaboration toward common purpose rather than competitive parallel programs that waste resources duplicating efforts. But the motivation exists. The questions matter. If interstellar visitors are natural, studying them tells us about planetary formation across the galaxy, about compositions and processes that occurred around different stars, about diversity of conditions that created the wandering population we're detecting. That's valuable science worth investing in. And if even one visitor turns out to be artificial, if we confirm technological origin for single object, the return on investment is infinite, because then we've answered the most profound question humanity has ever asked. We're not alone. Intelligence exists beyond Earth, and we have physical proof, hardware we can study, technology we can examine to learn about capabilities and materials and design principles that might teach us things we wouldn't discover on our own for centuries. That's the bet. That's the gamble the infrastructure proposals represent. Invest now in capabilities that might reveal something extraordinary or might just add to our understanding of natural processes. Either outcome justifies the cost. Either way we learn. Either way humanity benefits from expanded knowledge about the cosmos we inhabit. The classification system, the Loeb scale, is what ties everything together, provides the framework for deciding which objects get interceptor missions versus which get routine observation versus which get ignored because resources are limited and priorities must be set. Without classification scheme, without agreed criteria for what makes an object interesting, you can't allocate resources rationally. Can't distinguish between trillion natural wanderers and potentially small number of artificial visitors that deserve intense study. Class C objects get catalogued, added to database, tracked if convenient but not prioritized. Their baseline, confirmation that interstellar visitors exist and that our detection capabilities are working but not surprising, not worth major resource allocation unless they happen to be passing very close, or unless their trajectories make them easy targets for opportunistic observation. Class B objects get intense study with existing facilities, Hubble time, James Webb observations, ground-based telescope networks coordinating to track them continuously, spectroscopy to measure composition, photometry to track brightness variations, astrometry to precisely determine trajectories and search for anomalies. Everything we can do remotely to characterize them thoroughly and determine whether they're just unusual natural objects or whether they show features that push toward Class A. Class A objects, if we ever confirm one, get everything. Get the interceptor mission. Get the lunar eye pointed at them for maximum resolution imaging. Get international coordination and emergency funding and all the capabilities we can bring to bear on the most important discovery in history. Get studied so thoroughly that we extract every bit of information possible before they leave our solar system and the opportunity is lost. 3i Atlas sits in Class B. Suspicious enough to warrant intense study, anomalous enough that artificial hypothesis can't be dismissed, but ambiguous enough that natural explanations, however strained, remain viable. We need more data to push it toward Class C through better natural explanation or toward Class A through evidence that definitively indicates technology. And getting that data requires either lucky timing, catching it when it's optimally positioned for observation, or better instruments that let us see details we currently can't resolve. The vision that emerges from all this infrastructure planning, from the lunar eye and the interceptor fleet and the classification scheme, is of humanity transitioning from passive observer to active investigator. From looking at what the universe shows us, to reaching out and touching what we find. From accepting our blindness and ignorance to building eyes that can see and hands that can reach. This is active SETI, not just listening for radio signals like we've done for 60 years, not waiting for someone to call us, but checking the mail, going to the door, examining packages that arrive, determining whether they're just random debris or whether someone sent them deliberately and whether they contain messages we need to decode. The metaphor of cosmic Tinder that appears in the proposals is apt even if it's informal. We're evaluating candidates, swiping left on rocks, swiping right on anomalies, looking for the perfect match, The object that shows clear signs of intelligence, that provides the evidence we need to know we're not alone. That transforms speculation into confirmation and changes everything about how humanity thinks about its future. And maybe we'll find it, maybe among the trillion objects passing through our solar system, among the population we're only beginning to detect, there's at least one that's definitely artificial. That's obviously technology. That's been sent here deliberately by minds we've never encountered for purposes we can only guess at. Or maybe we won't. Maybe the population is entirely natural. Maybe every anomaly we detect eventually gets explained through exotic but conventional processes. Maybe the galaxy is filled with wandering debris but empty of wandering probes. Maybe we're alone in actively investigating the cosmos, and all the others, if they exist, are either too primitive to leave their planets, or too advanced to need physical probes, or too far away to have visited here, or simply non-existent, because life is rare, and intelligence rarer, and technological civilization rarest still. We don't know. Can't know from current data. Need more observations, better observations. Observations that require the infrastructure being proposed, that require investment and commitment and willingness to take seriously the possibility that some of what we're seeing might be artificial, even though that possibility makes many people uncomfortable. But the possibility is legitimate. The data supports it at least as much as it supports exotic natural explanations, and the questions matter too much to ignore just because the implications are unsettling. If there's even small chance that interstellar visitors include artificial objects, that the galaxy has infrastructure we're only now detecting, that humanity is late to a party that's been going on for millions of years, we owe it to ourselves to find out, to build the capabilities needed to investigate thoroughly, to answer the question definitively rather than speculating forever based on ambiguous data. The cosmic date happened. 3I Atlas came. Past is leaving. We saw it, measured it, documented its properties, and now we're left asking what it meant, whether it was random or deliberate, whether we were visited by debris or by messenger, whether the silence that accompanied its passage was absence of intelligence or presence of intelligence so advanced that it doesn't announce itself in ways we recognize. Those questions won't be answered quickly. Won't be resolved by single observation or single mission, will require the long-term infrastructure investment that the proposals outline, will require the lunar eye and the interceptor fleet and the classification scheme and the international cooperation and the sustained commitment to actually following through on building what needs to be built to investigate properly. But the questions will be answered eventually, because humanity doesn't give up on profound questions. Doesn't stop investigating just because answers are difficult or implications uncomfortable. We'll build the eyes to see them. We'll build the ships to meet them. We'll develop the frameworks to evaluate them. And one day, maybe in this generation or maybe several generations from now, we'll find the Class A object, the unambiguous case, the proof that we're not alone. And on that day, everything changes. Biology gets rewritten because life isn't unique to Earth. Philosophy gets transformed because we're not the only minds in the universe. Religion adapts or struggles as believers reconcile faith with confirmed existence of other intelligence. Politics shifts as nations recognize that we're not competing for dominance on single planet, but potentially participating in galactic civilization that existed long before us, and that operates according to rules we don't yet understand. Or maybe we find that the population is entirely natural, that trillion objects are all rocks and ice, that anomalies we detect all have natural explanations once we understand the full diversity of cometary behavior across different formation conditions, that we're alone after all, and the galaxy is ours to explore without needing to negotiate with anyone or follow protocols established by others who were here first. That outcome matters too, changes how we think about future. If we're alone, if intelligence is rare enough that we're the first in our corner of galaxy, then we have responsibility to preserve ourselves, to expand carefully, to seed the cosmos with life and mind, because if we don't, the universe remains silent. remains unconscious, remains without witnesses to appreciate its beauty and complexity. Either way, whether we find others or find emptiness, the investigation matters. The questions deserve answers, and the infrastructure being proposed gives us the tools to get those answers rather than just continuing to speculate based on insufficient data. As we close out 2025, as we look forward to 2026 and beyond, 3i Atlas is still out there, still moving outward, still carrying whatever secrets it holds. We'll track it as long as we can. We'll gather what data remains available before it fades below detection thresholds and disappears back into the darkness from which it came. But it won't be the last. The trillion object population means more are coming. More visitors will pass through. More opportunities to detect and observe and characterize. More chances to find the Class A object that changes everything, or to confirm that natural processes account for all observations and that our search continues. The era of passive observation is ending. The era of active investigation is beginning. We're building the infrastructure. We're developing the techniques. We're preparing for the possibility that among the cosmic visitors passing through, at least some might be messengers, might be probes, might be evidence that we're not alone and never have been. The sky is not empty. Every time you look up, you might be looking at traveler that crossed galaxy to be here, that drifted for millions of years through the void between stars, that carries information about other worlds and other systems and potentially other minds. 3i Atlas is fading, but the questions remain. The investigation continues, and the infrastructure that will let us answer those questions definitively is being designed and advocated and potentially built over the coming decades. We're not just watching anymore. We're reaching out. We're preparing to touch what we find. We're getting ready to confirm or refute the most important hypothesis in human history. Are we alone? The trillion objects passing through our solar system might hold the answer. And we're finally building the capabilities to find it, to reach out to these visitors and determine what they are, to classify them properly, to identify the rocks and the ice, and potentially, if we're fortunate or if the universe is more populated than we've dared hope, to identify the technology. The cosmic date happened. The relationship is just beginning. And what happens next depends on whether we commit to the investigation, whether we build what needs to be built, whether we take seriously the possibility that among the trillion wanderers at least some might be more than just debris. The answer is out there, in the darkness, moving past us right now while we debate and plan and slowly build the tools we need to reach it. The question is whether we'll move fast enough, whether we'll commit thoroughly enough, whether we'll actually follow through on the implications of what we're detecting. Because the cosmic date isn't over, it's continuing. More visitors are approaching, and each one is opportunity to learn, to discover, to potentially confirm what we've suspected and hoped and feared, that we're not alone, that the galaxy has been populated for far longer than we've existed, that intelligence is out there, has built things, has sent them across the void, and that some of those things are passing through our neighborhood right now. All we have to do is look and reach and touch and learn what the silence has been hiding all along. Stay curious, keep looking up, and remember, the trillion objects are there whether we see them or not. The only question is whether we'll finally open our eyes wide enough to recognize what's been passing by all along.